Hey, you guys, this is Miss Allday. We're getting ready for our second lesson in this chapter. We're going to do 9-2 today, reflections. Today is April the 15th, and we're going to start on page 554. If you want to open up your textbook, I'm going to make sure you know where the got it problems are. All right, so we're going to do reflections. When you reflect a figure, the shapes have opposite orientations. Okay, so they're opposite. Two figures have opposite orientations if the corresponding vertices, so we're talking about vertices like B, G, U. If the corresponding vertices of the pre-image, that's the original, and the image, which is a copy, read in opposite directions. So let's check this out here in this example. All right, so I'm going to do this in blue so you know where I'm at. This is triangle bug, B, U, G. All right, I went clockwise when I read bug, triangle bug. The reflection of triangle bug is triangle B prime, U prime, G prime. Now, triangle B prime, U prime, G prime reads counterclockwise. Watch this. B prime, U prime, G prime. That is counterclockwise. All right, so if you see two figures like this, a pre-image and an image, and you see that they read in opposite directions, then you can tell it's a reflection. Now, you can also tell that each of these are the same distance from this line right here. I'm going to make this line in blue. U is the same distance from that line as U prime is. B is the same distance from that line as B prime is. G is the same distance from the line as G prime is. And that's how it's going to be with a reflection. The pre-image and the image will be the same distance from the line that they are being reflected over. All right, let's look at some more information. When you reflect a figure across a line, each point of the figure maps to another point. That's what I just got finished saying. It maps to another point the same distance from the line, but on the other side. And that's what I just said. All right, so here's another. Don't forget that the orientation of the figures are reversed if it's a reflection. All right. Reflection across a line. All right, now in this picture, the line I'm looking at is this line right here, this blue line. You see its name is M. This is line M. So a reflection across line M is called the line of reflection. That is a transformation that has the following properties. So we're going to look at the properties that you have whenever you do a reflection. All right, the first one. If point A is on line M, okay, let's look at this. You see that point A is on line M? All right, then the image of A is itself. So I can't reflect A across a line that it's sitting on. So if A is on the line, then when it's reflected, A and A prime are actually the same point. Okay? All right, let's look at the second point. 2. If a point B is not on line M, okay, so let's go over here and look at point B, making it real big in blue. Then M, line M, is the perpendicular bisector of the distance between B and B prime. All right, so here we have, I'm going to do this in green. Here we have right here B. Okay, if you reflect B across line M, you're going to get B prime. So the distance from this line, B is the same distance from this line M as B prime is. You also notice that line M, I'm going to do this in green, okay, is actually the perpendicular bisector of the distance from B to B prime. So we could call that B prime segment. That's what they're referring to right over here. Okay, so if this is a reflection and B has been reflected and it forms B prime, then the line that it's being reflected over is the perpendicular bisector of the distance between the 2 points that are reflected. So, for instance, here's C. Okay, let's say C is 3 units from line M. All right, here's C prime. C prime is 3 units. So this is 3 and this is 3. Now I'm making up this number 3 just to show you that those are congruent distances from this line. So this is a perpendicular bisector. All right, so now let's talk about, well, what would it look like if they wrote it? You know how yesterday we did a translation, 4 units to the right and 2 down? We did it like that, and we're going to translate, we'll say triangle ABC, and it ended up equaling triangle A prime, B prime, and C prime. Okay, that's what we did yesterday, and that was pretty much what you call a rule. Let me erase that. All right, you write the reflection. There's a typo right here. You write the reflection across line M that takes P and reflects it to P prime as this. So the reflection, just like yesterday we did T for translation, the reflection across line M, that has to tell you the line they're reflecting it over. It's called subscript. It's below. It's kind of like when we did y2 minus y1. That 2 and 1 were called subscripts. So you put subscript below, you put the line that you're reflecting it over. So the reflection across line M of point P will result in P prime, just like we did yesterday, the pre-image and the image. So if I was going to do point C, I would say the reflection across line M of point C gives me C prime. Okay, kind of like a rule. All right, if you're doing your textbook, we're going to go ahead and jump to the next page, which is page 555. You can use the equation of a line of reflection in function notation. So for example, instead of saying that this was line M, if you were on a coordinate graph and you wanted to reflect it over this particular line, y equals x. Well, first of all, let's talk about that line for a minute. That's slope-intercept form. Y equals mx plus b. Since there's not a b, and don't write what I'm fixing to write, okay? This is the y-intercept. There's not a b, so that b must be 0. All right? So the b is 0. Now, in front of this x right here is a 1. Well, that's the slope. Slope is 1. See if I can find my eraser. 1. So that means rise 1, run 1, rise 1, run 1. So if I was doing this, which I'm not, so don't write this. If I was reflecting across y equals x, I would be reflecting across this line right here. And we can call it a dashed line if we want to, because it's kind of an invisible line. That's what you would be reflecting over if they told you that you were reflecting over y equals x. All right, let me erase all this because that's not what we're going to do for this next problem. I just wanted to make sure you knew how to create that line in case you do reflect over it. All right, so reflecting over y equals x actually describes the reflection across the line that it's going to be reflected over. All right, so we're going to reflect a point across the line. This is our first concept. I'm just going to put a number 1 here. So point P has the coordinate 3, 4. So go graph that. 3, 4, and label it P. All right, now let's look at the rule. I'm going to do the rule in blue. What are the coordinates, if this is the rule, that I'm reflecting across y equals 1, and I'm reflecting P? So I'm going to get P prime. All right, so We have P in the picture. We know what it is. There's point P. Now we have to do this line, y equals 1. Now remember Hoy. Horizontal, 0 slope, y equals form. Look, this is in y equals form. So this line that we're fixing to draw is going to be horizontal. So y equals 1. Go to the y-axis. Here's 1. Draw a horizontal dashed line. This is the line we are going to reflect P over. All right, now this is really easy. All you do, I'll do this in red, is you count. How far is P from that line? It's 1, 2 units, 2 steps. All right? Then what you're going to do is you're going to go to the line, and you're going to be opposite of that P, and you're going to go 1, 2 steps down. All right, I'm going to do this in green. This point right here is P prime. Make sure you can see that little prime mark. Prime. Okay, so I reflected point P over y equals 1, and I got P prime. Now, you don't have to write that. Okay, I was just showing you that's what the rule looks like. Now, what I want you to do is answer this question. What are those coordinates? So go to P prime, and P prime is 3, -1. All right, I'm going to use red this time. This is our got it problem 1 that you need to do. You can do it on a separate sheet of paper if you want, or you can just go ahead and just do these notes and just make sure maybe you highlight the got it problems for me. All right, so we're going to reflect over x equals 1. We're going to reflect point P again, and we're going to get P prime. So we're just pretending like this is another problem, but we're going to use the same graph. So we need to find x equals 1. All right, remember VUX, vertical, undefined slope, and x equals form. So this is an x equals right here. X equals 1. So we know that this is going to be VUX. It's going to be vertical. So we're going to go to x-axis. We're going to find 1, and we're going to draw a vertical line through that point. All right, so I'm reflecting over the x equals 1. I'm reflecting point P. All right, I'll use purple. All right, P is still 2 places from the line. It's not always going to be that way. So I'm going to go 2 units from the line this way. I'm going to do it in black. This is my new P prime for example number 2. So what are the coordinates? Well, let's look at it. P prime is -1, 3. Okay, so that's reflecting on an x, y axis or on a coordinate grid, whatever you want to call it. All right, let's move on to our next concept. Still on the same page in the book. You can also use the notation reflecting over line M to describe reflections of figures. So not just points, you can reflect the whole figure like we were doing yesterday. Also like we did right here. We're reflecting a figure there. Up here, we're reflecting a figure. It's not just a point. All right, the diagram below shows the reflection over line M of triangle ABC. And it also shows function notation and how it's used to describe some of the properties of the reflections. Now, note, the properties below mean that reflections are rigid motions. Remember, we talked about rigid motions yesterday. Distance is preserved and angle measure is preserved. Okay, so the shape is not changed and the size is not changed. The positioning is changed. Okay, all right, so here we go. I'm just going to underline as I talk about it. Reflections preserve distance. So I'm going to show you. If I'm going to reflect point A over line M, I'm going to get A prime. Okay, so here's A. Now remember, when it's on the line, you can't really reflect it. It is what it is. Point A and A prime are the same thing. All right. If I'm going to reflect point B over line M, it will result in B prime. So here we have, here's B. I reflected it. I got B prime. So the distance of A to B, so I'm just going to kind of do this in blue, distance from A to B, is going to be equal to the distance from A prime to B prime. Those are going to be equal. So you know what we usually do when segments are equal, we put a tick mark there. I'm going to put 2 because we already have 1 in this picture. All right, so that talks about distance, how distance is preserved. All right, now let's talk about how reflections preserve angle measure. Because remember, we're talking about these are rigid motions. Distance and angle measures are preserved. All right, if I'm going to reflect angle ABC over line M, it's going to result in angle A prime, B prime, C prime. And the measurement of those two angles will be the same. All right, so I'm going to do this in purple. If I take angle A, B, and C, and I reflect it over that line, and I get angle A prime, B prime, and C prime, then this angle will equal this angle. They will be congruent. So angle measures are preserved. All right, distance is preserved. All right, let's go to this last one. Reflections map each point of the pre-image, this is the pre-image, the original, to one and only one corresponding point of the image. This is the image. That means basically that if you're going to map, or if you're going to reflect A and you're going to create A prime, there's going to be one point that reflects it. B and B prime, there's one point that's being reflected. C and C prime, that's one point being reflected. Okay, so if you're going to reflect point A over line M, you are going to get A prime. If and only if the reflection of A prime over line M will actually give you A prime. So let's just say you started with B prime first and you reflected it and got B. Okay, it works both ways. If you reflected B and you got B prime, okay, you can switch them. Okay, like A equals B, and B equals A, kind of the same thing. But usually when you're reflecting, you name the new point, which is the image, something prime. But you don't always have to do that. Sometimes they'll just rename it. All right, let's go down to graphing a reflection image. This is going to be on the next page, page 556. All right, graph the points A, B, and C. Okay, let's start by doing that. A is -3, 4. A. B is 0, 1. It's B. And C is 4, 2. That's C. All right, so graph these points, and now let's connect them. Now this is when, if you don't have a different color, you're going to want to do this in a different color, or this is going to look confusing. Even if you do it like pencil and black or blue and black, just so you have some kind of different color. So I'm going to change up my coloring now. Because what I'm going to do, I graphed it. Oops, sorry, my paper went away. I graphed it. I labeled it. Okay, now we're going to reflect over the y-axis. Now find the y-axis and let's turn that into a dashed line. This is what I'm reflecting it over. This is the y-axis. All right, I'm going to reflect it over that. And what am I reflecting? I'm reflecting triangle ABC. All right, so what you do, it's real easy. You start with one point at a time. All right, we'll do this in blue. How far is A from 4? 1, 2, 3 steps, right? All right, so go 1, 2, 3 steps. Draw that point. That's A prime. You just reflected point A. All right, erase those markings so it doesn't look confusing. All right, now, do you see that B is on the line? When B is on the line of reflection, B is B prime. So I'm going to try to write a little B prime here. All right, now I'm going to reflect point C. All right, C is 1, 2, 3, 4 away. So I'm going to go 1, 2, 3, 4 away. All right, so right there. I'm going to erase those markings because we don't want it to look confusing. Okay, I just reflected that, and that's C prime. Now, connect them. A to B, B to C, and C to A. Now, you should be able to tell that that's a reflection, because if you actually colored in this piece, look, is that the same as this piece right here? You see that this piece here is the same as this piece here? This is how they do designs for t-shirts and stuff, you know, emblems, logos, that kind of thing. All right, so we did that. Now, this next one is going to be your got it problem number 2 right here. All right, we need to graph and label. We're going to go graph the same purple triangle that we did at the beginning. Okay, same triangle. Go graph this again. A is -3, 4. Label it. B is 0, 1. Label it. C is 4, 2. Label it. Connect them. Yours probably looks nicer than mine because you can pause this and go find you a straight edge or a ruler. But I can't do that. All right, so we graphed it, we labeled it. Now look, we're going to reflect it over the x-axis this time. Okay, let's use red. Let's go find the x-axis, and let's turn that into a dashed line. All right, reflecting over the x-axis. Okay, that means instead of me going from left to right or from right to left, I'm going to go from the top to the bottom. If you recall, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So I'm going to reflect quadrants 1 and 2 into quadrants 3 and 4. That was free. That didn't cost you anything. All right, I'm going to use blue now. Now, B is 1 unit away from the line of reflection. So I'm going to go down 1 unit, and I'm going to name that B prime. C is 2 units. So I'm going to go 2 units this way, and that's going to be C prime. Now, I always like to go back and erase those because sometimes that just starts making it look confusing. All right, A is 1, 2, 3, 4. So A prime is going to be 1, 2, 3, 4. It's going to be right here. A prime. I'm going to go back and erase those marks. Okay, now you're going to connect the dots. And now you have reflected triangle ABC over the x-axis, and you have created triangle A prime, B prime, C prime. All right. Let's go to the next problem. Writing a reflection rule. Example 5. On this one, in your book, it's problem number 3. All right, each triangle in the diagram is a reflection of another triangle across one of the given lines. Okay, you notice when I do the reflection lines, I do them dashed just to make it similar to the book so it keeps making sense. All right, for this A right here, in your book, this is problem 3. How can you describe triangle 2, I'm going to put a smiley face in it, okay, by using a reflection rule? Now, remember, the distance from one of the points here to one of the points there, this line would have to be perpendicularly bisected. Okay, and if it's being reflected over line K right here, you can look at it and tell that this little piece right, you can redraw it. This little piece right here is in no way, shape, or form equal to this piece right here that I'm squiggling on. There's no way. So we know that that's not right. Plus, if you look at the orientation of 2 and the orientation of 3, they didn't change. We know when you're reflecting, the orientation is going to change. All right, so we know it's not 3. All right, let's look at 2 and let's look at 1. Because this one looks like it kind of changed. Now, If it was being reflected over line K right here, you would see that it was a perpendicular bisector, and it's not. If it's being reflected over M, it kind of looks like it's a perpendicular bisector right here. Oops. Right here, right? Like maybe it crosses here, maybe this is equal to that, but I can't really tell. Plus, I don't know if the orientation is opposite. It just doesn't look like it is. All right, so let's go check out 4. We might come back to 1 if you feel like that's it. All right, so I'm going to go to the right angle because that's the easy part to find. And here's a right angle. All right, and I'm going to go like this. Aha, look, that is a perpendicular bisector. Yeah, that makes perfect sense. And we could even map more points. I'm going to erase my smiley face. And I'm going to map going from this point to this point. Yep, perpendicular bisector. All right, we can do it again. We can go from here to here. Yep, perpendicular bisectors. Now, you don't have to write all that busy stuff. Just at least have one there. That's the easiest one to do, so that's the one I would do. How can you describe triangle 2 by using a reflection rule? All right, so this is what we're going to do. A, we're going to put A below. We're going to say that triangle 2 equals a reflection over line K of triangle 4. Now, would it have, they said, how can you describe triangle 2 by using a reflection rule? So they wanted us to describe 2, so that's why I started with that one. Okay, but really you could have written this way. You could have said the reflection over K of triangle 4 equals triangle 2. 2's the one they just wanted a description of. All right, so either way is fine. All right, now let's look at the next problem. This is your next got it problem. I'll do this in green. So B is your got it problem from the book. It's got it problem number 3. All right, it says, how can you describe triangle 1 by using a reflection rule? All right, I'm going to use reds. Put a little smiley face here. That's what I'm looking at. So you're like, well, I can already tell. Look, it's this one. That's the same distance. Perpendicular. Both equal. You could go over here and do it. You know it's going to cross here. And these are going to be equal. You could do the same thing to this point here and this point here. But it starts getting really busy. So let's just choose those 2 to do. All right, so for B, they want to know how can you describe triangle 1 by using a reflection rule. Okay, so triangle 1 equals a reflection. Now, what line is that across? It's across line M. And what triangle is reflecting, forming 1? That would be triangle 3. Now, remember, you could switch the sides just like I did a while ago if you wanted to. So we used a reflection rule to describe triangle 1. All right, there's another thing I wanted to mention to you. Don't worry about writing this, okay? If you wanted to show that it has opposite orientations, you could like name this A, and you could say, okay, well, this is A prime. You could like, okay, let this be B. Well, that means this is B prime. Well, you're like, okay, let this be C. Well, this is C prime. All right, so ABC clockwise, ABC counterclockwise. Just to kind of review that that's something we also said. All right, let's go down here to example number 6. My board's acting funny on me again like it has in the past, but that's all right. This is actually in your book, problem number 4, and it is located on page 557. Page 557. This is the last one. Using properties of reflections, and I just copied and pasted directly from the book. So I'm just going to walk with you through this because I didn't want you to have to copy all this down if you ended up like copying your notes. In the diagram, a reflection of G over line T gives me G. So see right here, look. When the point is on the line, you don't really reflect it. It really is what it is. It's itself. This is when it doesn't let me erase. It's all right. All right, so a reflection of H, point H, over line T is J. Okay, so H and J are reflected. That means this distance is the same as this distance. All right, and the reflection of point D over line T is D itself. Okay, so we know now that that's really a perpendicular, right? Perpendicular bisector. Use the properties of reflections to describe how you know that triangle GHJ is an isosceles triangle. Well, since G is reflected and you get G, it's the same point, kind of like reflexive property, right? And when H is reflected and you get J, that means they're the same distance from each other. And reflections preserve distance. We know that if I reflected segment GH over point T, that I'm going to get segment GJ. So that means this distance GH and this distance GJ is also preserved. So GH equals GJ. And by definition, that makes an isosceles triangle because you have two sides that are congruent. All right. Now, this got it number 4 is your got it problem. Can you use properties of reflections to prove that triangle GHJ is equilateral? Now think about this. Do we really know anything about this being equal, HJ? Do we know that HJ equals GH or GJ? We don't. Okay, so can you use properties of reflections to prove that? No, we cannot. Okay, well, let's put why. Well, it is not possible to prove that triangle GHJ is equilateral since you cannot prove that, I'm going to do this in a different color, HG, you cannot prove that HJ equals HG, or you cannot prove that HJ equals GJ. All right, and that's the end of this lesson. All right, this homework is not the right homework. I'll put your problems down here. Your homework, which are what I call your practice problems, you're going to do problems 1 through 3. Then you're going to do number 7, 11, 13, and 17. So this is going to be page 557 to 558. You get 1 point for each problem you do. So this is 1, 2, 3, 4, 5, 6, 7 practice problems. And then you have, 4 got it problems. So this is going to be worth 11 points. All right, and you're going to take a picture of all these notes if you did that, or just your 4 got it problems and your 7 practice problems, and upload that to the same assignment. All right, you guys, have a good evening. Talk to you later. Bye.